Okay, all right. So the title of my talk today is Real-Time Search Infrastructure at Twitter. Let me start off by telling you a little bit more about myself. So I'm an associate professor at the University of Maryland. I had the pleasure and the fortunate opportunity of spending an extended sabbatical at Twitter from 2010 to 2012, so I just returned to the university. So I'd like to say that, I came out of the ivory tower onto the factory floor, where I spent 2 years basically working as a software engineer, building shit that works. Okay, all right, so that's sort of a little bit of the context and the background. Today I'm going to be talking about real-time infrastructure. So the focus is going to be on infrastructure as opposed to relevance. I think honestly speaking, at Twitter, we have a lot more to work on in terms of relevance. So I wanted to share the work that we've been doing in terms of infrastructure. So I am up here and I get the benefit of sharing a lot of, I think, cool technology with you, but the acknowledgments really do go out to the search relevance and search infrastructure team that make this possible. Okay, all right, so let's start by talking about big data. So big data sort of entered the consciousness of everybody in the last few years, and it's perhaps best represented by this animal. So Hadoop has sort of emerged as a de facto platform for processing and analyzing large amounts of data, and it's represented by an elephant because it's a mascot of Hadoop. But that's not what I'm going to be talking about today. So the focus of today's talk is going to be on what I call fast data. So high velocity data, data that's moving at you pretty quickly. All right, so why is this important? Well, it's important. I think it's fairly obvious. I think Twitter is sort of a very nice real-time source of information where people get their news, right? So Twitter is now becoming a source where news breaks. Right, so perhaps the earliest example of this goes back to 2009. This is one of the best examples. So on January 2009, US Airways flight 1549 took off from LaGuardia Airport. Shortly after it took off, it struck a flock of Canadian geese, causing both engine failure. And later on, it actually gently landed in the Hudson. Today, we know this sort of episode as a miracle on the Hudson. This incident broke out over Twitter, right? So the news broke over Twitter. Somebody was taking a ferry across the Hudson River and saw the plane land in the Hudson, right? So this is sort of a very, I think, very great example, very early example. This was all the way back in 2009 of sort of the power of Twitter breaking news. Okay, here's another fun example. So in August 23rd, 2011, there was a smallish earthquake, magnitude 5.8 earthquake in Virginia, and I live close to Washington, D.C. around here. And so if you sort of measure the major metropolitan area, this is about 300 miles to New York, right? Okay, so because of that, we have this cue video. We had some fun with this. There's a very nice touch. Did people notice what he was reading? Okay, it's a cultural meme also. Anyways, so I thought that was really fun because if you actually go back to the Twitter stream, you can actually find instances of people saying, earthquake? What earthquake? And then, a few seconds later, oh, that earthquake. So I think this is sort of a nice, fun illustration. And of course, this video is completely apocryphal, but it really nicely illustrates the speed at which information is moving. Okay, so Dick Costolo is the CEO of Twitter, and he likes to say this, so the mission of Twitter is to instantly connect people everywhere to what's most meaningful to them. So to me, from a technical challenge, there's sort of 3 technical challenges. So number 1 is that everything has to happen in real time. The second is everything has to happen at scale, right? So we want to connect everybody. And third, from the IR perspective, is meaningful is talking about notions of relevance, Right, so I think from a technical perspective, these are the things that interest us the most. Doing things in real time, doing things at scale, and then having some notion of relevance. Okay, so I want to go into this a little bit more detail and sort of try to characterize, how fast is information moving on the Twitter stream. And so we'll start off a few stats, right? So everybody knows Twitter's 140 characters. I think the public stat we share now is about 200 million active users and then collectively posting about 400 million tweets per day. So you can sort of divide through and get a sense of the average tweets per second that's being tweeted. There are, of course, spikes, and so there was a record of around 26,000 tweets per second so Japan is one of the really big markets. And I think in this particular case, there was a coordinated effort to sort of try to break Twitter. And I think we were pretty proud that we survived this attempt. Okay, but let's take a look at speed in a different way. And so I want to share with you a study we did last year that tried to characterize this notion of churn. And by churn, I mean sort of terms and queries that sort of rapidly become prominent, sort of come into the limelight and sort of fade away. This sort of natural media cycle, and I sort of want to try to quantify that. Okay, so this was published with Gilad Mishneh in ICWSM last year. So here's what we did. We took a look at queries and also tweets. What we did is we looked at a particular interval and the interval after that. So the interval was either hours or days. And we did two things. We computed a very simple metric that we called churn. And so churn is the fraction of terms that in particular interval, t, that are no longer observed in t plus 1. Right? So if you have a churn of 1.0, that means all the terms are different. Right? And a churn of 0 means everything is static. And naturally, it's going to be something in between. So that's one metric. The other was we computed KL divergence between each interval and every subsequent interval. Right? Okay, so here's some results in terms of daily. So KL divergence on a day-over-day type calculation. Right, so we have tweets, we have queries, and then we have also query unigrams. Right, so breaking up the long queries, multi-token queries into the component unigrams. So these are the results on a daily basis. These are the results on an hourly basis. Is actually somewhat more interesting because you see sort of the very nice pattern, the daily variations in terms of tweets, also the daily variation in terms of queries, and slightly sort of not a particularly strong daily signal in terms of query unigrams. So here are the interesting statistics in terms of churn. So let's take a look, for example, at this line. So if you take a look at queries and subtract out the trends, and let's say you take a look at the top 1,000 terms on a day-over-day basis. So this is, for example, telling us that of all terms that we observed in one day, in the top 1,000, 32% of them are no longer there the next day. All right, so if you look at an hourly basis, for example, and you take a look at, let's say, the top 100 terms, subtracting out the trends, you have a 28% difference. So it actually tries to quantify this notion of how fast these conversations on Twitter are evolving. Okay, so here's a case study. So during the period that we're looking at was October 2001. Steve Jobs passed away. So Steve Jobs, co-founder and former CEO of Apple, right? And so here's a sort of a very nice characterization of sort of what happened then. In the red line here, you see sort of the daily cycle of the KL divergence of a typical day, right? So it just follows the rhythm of the general day. And in the blue circles, what happened the day Steve Jobs passed away. So what you see here is a huge drop. Now, this is sort of, why was there a drop? Well, it was dropped because that sort of took over the conversation, right? So those memes that talking about Steve Jobs sort of took over the conversation, and so the KL divergence dropped. You can sort of like think of the whole Twitter sphere sort of snapping to attention and discussing this. All right, so in the bottom here, I've just plotted out frequency. This is actually absolute frequency of various sort of queries on Twitter search. And so the query Steve Jobs itself started as a negligible fraction of the entire query log to, it's way off the scale. It's actually about 15%. So in a short period within minutes, it sort of churned into the limelight and actually accounted for 15% of the queries during that time. And then you can see other queries that sort of came in, and you see their prevalence. So you have Apple, Bill Gates, because Bill Gates is always compared to Steve Jobs. I think Pirates of Silicon Valley was sort of a meme that started at the same time. Stay Foolish is sort of Steve Jobs' motto. Pixar, one of his other productions. Okay, so what does this mean? So from the information retrieval perspective, I mean, we care a lot about term statistics, right? I mean, that's sort of our bread and butter. And so the implication from this is that modeling term statistics for relevance modeling is very difficult. So that means we need to have fine-grained temporal resolution. And so that's one point. And the second is that if you sort of look at the patterns of sort of prominence, rise and fall of query terms and term frequencies, simple decay models aren't enough, right? So attempts to, for example, model these sort of spikes as like an initial spike and exponential decay are oversimplified because real distributions don't happen that way. So those are sort of two takeaway implications. And from an infrastructure point of view, I think this is sort of the most important takeaway message, right? Infrastructure, you have to be able to handle low latency updates. Okay, all right, so what this means is that sort of the standard architecture that has evolved to deal with big data is actually very insufficient for these types of needs. Right, so the standard architecture for many internet companies, especially startups, is something that looks like this. On the front end, you're running something like Churn MySQL, and then on the back end, you run Hadoop, some type of Hadoop analytics stack. In our case, we run a Hadoop stack where with most of the analytics written in a language called Pig. It originally came out of Yahoo and now an open source project. And so you would sort of have something like a data import cycle that takes data from the user-facing services from the front end, moves it over to Hadoop. You do the analytics process in batch processing, and you push out a data export. Right? So this type of model becomes way too slow. Okay, and so we have a forthcoming paper in Sigma that's going to be presented in a couple months that exactly is a case study in the context of real-time query suggestion. Right, so we actually started building a real-time query suggestion a system that worked like this, right? So you had query logs, you import them into Hadoop, you do some crunching, build some models, and push the model back out. We discovered that was actually just way too slow. It was too slow to react to the churn of these query terms on Twitter. And so that's why we basically had to rewrite the architecture, and this is sort of tells our story of how we learned these lessons. Okay, all right, so let me move on and talk about something different. So Twitter is supposed to tell you what's happening, right? And to figure out what happened, obviously we need search. And of course, this being the ECIR community, the R community, and we have to talk about search, right? Okay, so I'm going to present this work that was published in ICD in 2012 about Twitter's real-time search infrastructure. Okay. All right, so let me start off with some statistics. Twitter is currently serving about 2 billion queries per day, about a 50 millisecond query latency, and about a 10-second indexing latency. That means from the moment that a tweet is published to when it is searchable on Twitter. As you'll see, most of that latency is actually in the ingestion pipeline. Indexing itself takes a very short amount of time, less than a millisecond. Okay, so what makes this different? I like to say, this is not your grandfather's IR. Well, it is like traditional web search in that we have low latency, high throughput demands, and like most commercial search engine companies today, we deal with that by putting our indexes in RAM so nothing really ever hits disk. Right, so that's sort of similar, but there are actually sort of some differences also. Right, so unlike most web search, with the exception of news search and a few specific verticals, we have this demand for very high ingestion rate and immediate data availability. All right, so once again, with the exception of some verticals like new search, when you're doing web search, you can sort of play off latency and throughput by sort of batching up documents and then doing batch indexing. Depending on the type of data, and an indexing delay of minutes, hours, or even days might be acceptable. Right? Whereas for tweets, they really need to be immediately accessible. Right. The second is because of this immediate data readability requirement, there's a strong requirement for concurrent reads and writes. So in a standard sort of web setup, what you can usually do is play some tricks with like an active index and let's say like a shadow index, and then you atomically flip them over. So you can arrange your architecture so that you're never sort of concurrently reading and mutating the index at the same time. Whereas that's sort of quite tricky to get around for us. And then finally, in our case, in the Twitter case, the temporal signal is something that's very dominant and very important for us. And once again, with the exception of something like new search, it's not a particularly strong or important signal in web search. Okay, so here's the sort of the architectural diagram of how everything sort of fits together. There's sort of the Twitter service. The tweets get pulled into an ingestion pipeline, and this is where you do things like tokenization, language ID, a few annotations, and sort of the tweets move their way through this ingestion pipeline, and then the tweets get pushed out to the early bird in-memory index servers. All right, so these are sort of the core retrieval engines that sort of power the service. And in the front end, there's these services called Blender, which are sort of like the brokers, and these serve as the service endpoints for the active user, for the end user. So this is a user using the twitter.com site or iPhone client or something like that. Okay, and we also have this thing on the side, the updater, which pushes real-time relevant signal from the site into the indexes. Okay, so what is early bird? This is what I'm going to be focusing on. So what early bird is Lucene with real-time extensions. Okay, so every time I say that, I sort of get this question. I mean, seriously, Java? And if there's sort of alcohol involved, it's, dude, seriously, Java? Okay, and I say yes. And this is sort of like a curious choice, right? I'm talking about performance, so why Java? There are actually some very sensible reasons, right? So one is it takes advantage of existing Lucene code base, right? So a lot of us at the IR community sort of thumb our noses at Lucene, but actually it's fairly reasonable, and the open source community has sort of spent a lot of effort on it. And so, let's take advantage of the existing code base and not try to reinvent a lot of the wheel. So that's number one. Number two is that Twitter runs a JVM-centric development platform. And so that means, JVM languages like Java and Scala play very nicely within this environment. And second, as I'll come back to a little bit later, Java has actually a really good and easy to understand memory model for concurrency, which actually makes a lot of the concurrency issues easier. Okay, all right, and so yes, but in Java you need to be careful about things like garbage collection. But other than that, I think it is actually a fairly reasonable choice. And so basically, early bird, this core retrieval system, is simply Lucene with real-time extensions. So for the purposes of this talk, I'll just assume that early bird executes Boolean queries and returns results sorted in reverse chronological order. So in the real deployed system, there actually is relevance and relevance ranking, but for the simplification, I'll just talk about executing Boolean queries and sorting the results in reverse chronological order, right? Okay, right, so the approach here is early bird provides, so Lucene itself provides implementations of, early bird provides implementations of the indexing and writing abstractions, and that basically just hooks into the Lucene code base, and we basically use Lucene out of the box to handle everything else. Right, so it's a very nice abstraction provided by Lucene that we take advantage of. Okay, so what's interesting about this particular approach? Well, so recapping the requirements, we need both high TPS, so that's tweets per second indexing ingestion, and also high QPS, right, queries per second on the retrieval end. Okay, so I think two interesting aspects I'm going to discuss are going to be the index organization to support these real-time index updates, number one, and number two, how we manage concurrency, so multiple readers and an index writer mutating the same index structure. Okay, so the high-level strategy here is we want to keep everything in memory. We want to limit the scope of concurrent operations, and that will become clear what I mean in a sec. And so we want to have a single writer, multiple reader approach. So indexing is going to happen on one thread by one indexer, and then the query evaluation is going to happen scale out with multiple threads. Okay, so that's sort of the general approach. Okay, so what actually ends up happening is you sort of have like almost like a federated index within a single server, right? So here's a general architecture. I'm zooming in on a particular early bird instance here, right? So this is a core index server. And so what happens is each one of these machines actually has a whole bunch of index segments, right? So there is one active write-friendly segment. These are, this is where tweets are being actively ingested, and then a whole bunch of sort of optimized read-only segments. And so what happens is that tweets are indexed in this active segment. Once this segment is full, we basically close it off and becomes read-only. And so you can sort of see it as sort of like a conveyor belt that moves backwards. So what this buys us is that it limits the scope of concurrent operations, right? So this is the only segment, index segment, in which you're doing active mutation of the data structures and also query evaluation. Everything else is read-only. Right? And so on the query evaluation end, you basically have a broker system where you have to do federated search across all of these and to return the results. Okay. All right. So the current stat we provide is each one of these servers has about 12 of these index segments. Each of them holds a relatively modest amount of tweets, 8.4 million tweets. Okay. And then of course, the index segments has both dictionary and a postings list, right? Okay, all right, so backing up a sec before I go into this, just sort of very quick overview, Boolean retrieval in a nutshell, right? So what do you do for Boolean retrieval, right? The first is you have to go into your dictionary and look up your postings, right? And then after that, you have to traverse the postings somehow. Right, so you traverse the postings with respect to what Boolean operator you're executing, right? So if you're doing an AND, you're doing intersection. If you're doing an OR, you're doing a union of postings, right? So conceptually very simple. Look up postings, go down the postings, apply ANDs, ORs, or NOTs, right? Okay, so the dictionary is pretty straightforward, just sort of a few minor tweaks. So the most naive implementation would be something like Java's hash map, but it actually doesn't work very well because of Java's default chain hashing implementation causes a lot of garbage to be collected and is just way too slow. So the solution is pretty straightforward. So we have a custom solution that uses open addressing instead of hash chaining. And as you would expect, it maps from string terms to term IDs, and we try to pack everything densely in parallel arrays, right? So in these parallel arrays, you do the mapping from term to term ID. It holds some metadata like number of postings, pointer to the tail of the postings list that serves as the entry point for query evaluation. Okay, there is a minor wrinkle here. So what about the index organization? Right, so we want to return results sorted in reverse chronological order, right? So that means it would be desirable in order to traverse postings in a reverse chronological order. Right, so, okay, so you open up an standard IR textbook, and it'll tell you that there are two primary organizations of index structures, right? So you can build a document sorted index, and that generally goes with something like document at a time query evaluation, right? Or alternatively, you can build something like an impact sorted index, and that generally goes very well with term at a time query evaluation strategies. Yes? Okay, so you sort of look at this and say, yeah, I don't think it makes sense to build impact sorted indexes, so we're going to stick with sort of document sorted indexes. Right, so as tweets are being ingested, we'll just assign them, monotonically increasing document IDs, and sort of that will be the index. That will be how we throw things into the index. Okay, now to sort of satisfy the desiderata of real-time search, there are a couple alternative ways you can organize the index structure. Right, so here's one approach. Well, so here's a term, and here's a posting list, and what you can do is you can insert postings sort of at the end, so you just add postings to the end, and then to support a reverse chronological traversal order, you sort of start at the end, and you sort of traverse the postings backwards. Right, so that's one organization that will make sense. Here's another organization that kind of makes sense. Right, so instead of adding postings to the end and traversing backwards, well, what you can do is you can try to add postings backwards so that you can traverse forwards to get the right order. Right? That seems like another reasonable way of organizing your postings list. And then finally, here's an alternative one, and this one's a little bit tricky, but I think it's workable also. Right? So you insert postings towards the end, and then to do query evaluation, you sort of guess an entry point, and that allows you to maintain a forwards posting traversal order. Right? So, so these are sort of three reasonable ways of organizing postings lists, and as it turns out, we end up adopting this approach. Okay, so the implemented solution is actually fairly simple. So in early bird case, each posting is simply a 32-bit integer. Okay, so we save 24 bits for encoding the document ID and 8 bits for holding the position. So as it turns out, tweets have a limited length, right? And so this actually is enough to hold positions. Okay, so postings lists are simply integer arrays, right? So we simply allocate an integer array, and indexing is simply writing ints into this element, into this array. So you're inserting elements, and that's simply indexing, right? You're writing postings. This is simple. It works well. It's simple. It's fast. It's very cache friendly because you're always writing in a predictable way. We're not using compression, but that's actually okay. Because if you recall, we have the active index segments that's write-friendly and all the optimized read-only, right? So because of the relative small size of these index segments, a particular index segment doesn't actually stay that long in an uncompressed state. So once we sort of fill up the index segment, we can then go back and optimize the layout. Right. The other advantage of this is that every element can be an entry point for posting traversal. Right? It's not like P4 delta or any of these block-based compression techniques where you can't arbitrarily, well, to access a posting list, you have to decompress entire blocks. Right? So we can access the postings list at any time, and as a result, there's no need for auxiliary data structures like skip lists or anything like that. Okay, so that's actually a nice design. However, the issue here is, what about this postings list allocation policy, right? What if we run out of space for sticking postings in postings list? Right, so the answer is we need some type of a block allocation policy. And the best way I like to describe it, this is sort of like a Goldilocks problem, right? All the story of Goldilocks and the three bears, right? So there's a too big, right? So if you allocate too much space, then you're wasting space quite naturally, right? The other end, if it's too small, then you're wasting time because then you have to do memory allocation, and memory allocation is relatively costly. And also, if you set the allocation policy too conservatively and too small, you also do waste space because what ends up happening is you have all these discontiguous slices that you have to somehow link together, and those linking pointers actually take up space. So imagine in the extreme end, you're allocating one posting at a time. Then you basically have a linked list, and you're wasting a lot of the space in the next pointers, right? Okay, and so we want to get things just right, right? So we don't want to be too aggressive and waste space. We don't want to be too conservative because that wastes space and is slow. We want to sort of find a middle ground. Okay, so here's a solution that we came up with. So what we have is a large set of 4 memory pools. So these are, you can imagine them as just unbounded integer arrays that will grow. And in reality, we allocate them in very, very large blocks, but you can just imagine them conceptually as an infinite array. All right, so what happens is these pools have fixed slices and fixed sizes. So in the first pool, each slice is 2 to the 1, the next one's 2 to the 4, 2 to the 7, and 2 to the 11. All right, so what happens is the first, when a new term is encountered, you allocate space, postings list, for the first 2 term instances, okay? And so you fill it up. After you exhaust a slice there, what you do is you allocate a 2 to the 4 slice in the next pool, and you continue indexing and fill it up. Once you get done with that, you allocate a slice in the next pool that's 2 to the 7, and you continue filling up that. And then you get to the end of the final pool, you allocate a postings list in blocks of 2 to the 11. And once you fill that up, you just continue allocating in this. All right, and then when you get to the end, there's essentially a postings tail pointer, and this is what's stored in the dictionary, right? So going backwards, when you're doing query evaluation, you look up in the dictionary the postings tail pointer that tells you that you're here, and this is where you start the query evaluation traversal, right? So you traverse backwards. Okay, so one question you might ask is, why 4 pools? And why these particular settings? What's so special about 2 to the 1, 2 to the 4, 2 to the 7, 2 to the 11? In fact, there is nothing special. We recently put out a paper that's currently on archives that does explore this setting, the trade-off space in terms of the number of pools in these slices, and sort of effectiveness, efficiency trade-offs. Okay. Right, so this is the active index segment. Once these index segments fill up, this is a diagram I had previously, right? So once this index segment fills up, we close it off and then sort of turn it into optimized read-only segment. And this is fairly not particularly interesting, but it's what you would expect. Right, so you optimize the active index segment after it stops new tweets. And at that point, since it's only going to be read-only, you know exactly how much space it's going to take. Right, so we divide things into short postings lists and long postings lists. For short postings lists, we simply reverse the postings but leave them uncompressed. For long postings lists, we reverse the ordering and implement some type of, it's basically an induced standard delta or gap compression, and it's basically a variant of P4 delta, simple 9, that type of family. Okay, the other interesting aspect I want to talk about is concurrency management, right? So here's the issue here, right? You have multi-threaded concurrent query evaluation in indexing, and although we've tried to simplify it, right, we've simplified it somewhat by isolating the concurrent operations to the single active index segment, and then we have a single index writer thread for indexing and multiple reader threads for query evaluation. There's still some complexities. Right. So just to set up the background a little bit more. So here's basically the very quick indexing overview. Right. So when you're indexing a tweet, for each term you look up the postings tail pointer and then you insert the postings. Right, so this is how you process all terms, and then you sort of increment this counter, which is called the max doc, which is the most recent document that you've encountered so far. Okay, so, and the consistency model that we want to guarantee that the search results are correct is something like this, right? We want to guarantee that the search is correct over all tweets less than equal to this max stock, right? So this max stock is just this monotonically increasing counter that says, this is the latest tweet I've ingested, and the search should be correct with respect to this, this max stock counter. Right? So this is actually quite a challenging problem, right? Because in a multi-threaded execution environment, you have arbitrary interleaved thread execution order, and particularly with multi-core processors, you actually have no guarantees when memory writes are visible to other threads unless you do something special. Right, so there's 2 aspects of concurrency we need to worry about within a posting list and across posting lists so that the query evaluation will be correct. All right, and whenever I talk about concurrency, I can't resist showing this picture because if we're not careful, we get into a situation that looks like this. Okay, all right. So what's the standard way of dealing with concurrency, right? You introduce some method of synchronization, right? But the problem here is that synchronization and speed are often enemies, right? Synchronization is generally costly and it slows things down. And so one of the things that was tried early on was to do heavyweight synchronization, right? So that's to make indexing atomic. So something like before you index a tweet, you basically lock all the postings, right, and then do your postings, whatchamacallit, insertion, and then unlock all of them by making the indexing operation atomic. But that was way, 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 way too slow. And so the early bird approach, the approach that was actually adopted later, is very lightweight synchronization using memory barriers. So in Java, there's this thing called the volatile keyword, which creates a memory barrier, and it guarantees that once you cross the memory barrier, your rights, your memory rights, are guaranteed to be up to date with respect to other reads, right? So, however, there's still an issue here that query evaluation is still potentially interleaved with indexing. So here's a very classic case, right? So what if your query is A and B, and at the same time you're ingesting a tweet that has A and B as those two terms? It could be issuing the query in the middle while you're only indexed A, but you haven't indexed term B yet. Right, so that causes some potential issues. And basically the way we go around it is, in short, we find all the possible cases in which these orders can be interleaved and hard code special cases and hard code the corner cases for that. So you sort of work out in pencil and paper, there are not that many special cases, and it's sane to be able to handle that. Okay, so I'm going to offer some performance metrics. This is also reported in the ICD paper. So just as a figure, as a source of comparison, the previous search system was MySQL as an inverted index and with Ruby on Rails as a front end. A very interesting choice for an architecture of a search engine. But when it started in 2008, it was ingesting about 20 tweets per second and serving about 200 queries per second. The team was able to scale up such an architecture to just before it was retired in 2010, serving about 12,000 queries per second and ingesting 1,000 tweets per second. Not bad for an architecture based on MySQL and Ruby on Rails. Okay, so with the recent early bird, with a more up-to-date early bird architecture, the standard server is something like a dual quad core, each with 72 gigs of RAM. We save something like 64 gigs for the JVM and the rest for the OS. A fully loaded active segment, so this is the segment that's actively being mutated and read from, takes about 6.7 gigs of RAM and is able to serve about 17,000 queries per second. Now, a fully loaded server, you fill up all the RAM, all the index segments, holds about 144 million tweets and can serve about 5,000 queries per second. At the same time, we're able to achieve about 7,000 tweets per second indexing load under heavy load. So we just test that by ramping up the query performance and trying to ingest tweets as fast as we can. And the index optimization, as you would expect, you get a fair bit of space savings. Okay. All right, so let me start wrapping up now. I want to sort of talk about what's next. So I started with the slide, real time, scale, and relevance. I want to talk about some of the things that we're working on. So in relevance, there's of course, tweet ranking. We've been working on that a while. There's still a lot to do there. The next two are sort of standard classic web search ideas, but with a twist. So doing query suggestion, but doing it in real time. Doing type ahead, but doing it in real time, right? So ECIR is happening in Moscow now, so maybe if you type in hashtag ECIR 2013, it would suggest Moscow as a potential query completion or something like that. Being able to do that in real time, I think, presents a new dimension. We're also doing what we call universal search, which is basically vertical fusion. So if you go to, like on your iPhone, for example, the search results page, and you type in a query like hashtag ECIR, you'll see photos that are interspersed with the stream of tweets. So I think that's fairly interesting. In terms of other work we're doing on this, what we sort of call discovery, right? Surfacing relevant content to the user. So a lot of that involves things like user modeling, graph services, so providing services to the interest graph, and then sort of this idea of universal discovery also. It's kind of like vertical fusion as applied to discovery. There's still plenty of more work to do in infrastructure, and so one of it is the ability to gather these real-time signals and to be able to push them out as part of, to be used in the online ranking algorithm with very, very low latency. So that's sort of one active area that we're continuing to work on. And then archive search. So there's always been limited on how far back you can search your tweets, and we want to be able to let users search older content. And so that brings in a whole host of architectural challenges as well. And then finally, there's always sort of the anti-abuse effort. And I think this is very challenging because this also needs to be in real time, right? It's not like in spam, like email spam, where you only need to get to it before the user opens his or her inbox, right? The time window in which we have to intercept spammy tweets or any type of content is very, very short. Okay, and that's about it. So I have a few questions left, a few minutes left for questions. I'll be happy to take your questions.